so welcome everybody. Sorry for a small delay due to technical problems. It's my pleasure today to announce our speaker, Piotr Kuc. He's a master's student, first-year master's student of mathematics at our faculty. And despite a young age, he's got already a result in a decent journal. But now he will be talking about a different result, which is Outdegree conditions for directed cycles. Please, Piotr.
Hello, everyone. Yes, so thank you for the introduction. So, as Andrzej mentioned, we will be talking about our Outdegree conditions for directed cycles. This is based on joint work with Andrzej himself and Justyna Jaworska. Okay, so let's get to preliminaries. We'll be discussing, as the title suggests, we'll be discussing directed graphs. A directed graph is, of course, just a collection of vertices and collection of edges such that are ordered pairs, right? UV, edge from U to V. And when we will be referring to graphs, we will be mostly referring to graphs that are oriented, meaning that there are no loops, meaning that there are no cycles of length 2. If there is an edge from V to U, then there will not be an edge from U to V. Okay, so we do not have arrows going both ways. And if we will be told, whenever I will say a graph, I will mean an oriented graph. Our results are based in the oriented setting. Sometimes I will be using a directed graph, but unless I specify otherwise, it's going to be oriented. And to define Outdegree, which will, of course, help us in understanding the nature of the paper, I will have to define an out neighborhood, which is simply just for a vertex, I look at all the neighbors from this vertex, all the neighbors of this vertex, meaning I look at for a vertex U, I look at all the vertices V, such that there exists an edge UV. And the set of all these vertices V is an out neighborhood. The size of the out neighborhood is the Outdegree. Similarly, in neighborhood will be analogously defined with in degree as well. Okay, so and in neighborhood will be a set of vertices V such that there is an edge V to U. Okay, and the minimum Outdegree is simply the minimum of all these sizes of out neighborhoods. Okay, minimum in degree respectively will be minimum of the sizes of in neighborhoods, while the semi-degree will be the minimum of both of these. Okay. Essentially, whenever we will be saying a minimum Outdegree equal to D, that means that every vertex has at least D out neighbors, and that's the important part of it. Okay, so I think the preliminaries are defined. Now let's get to the structures we'll be discussing. As the title suggested, we'll be considering mainly cycles, in fact, the directed cycles, which are simply a collection of vertices which are different, and which is basically a sequence of different vertices such that there is an edge from every previous one to the next. Okay, so from Vi to Vi plus 1. And of course, also from the last to the first, because it's a cycle. Yeah. We also will refer to a graph as free of some structure, as in fact, in our case setting, just a cycle of length L free if it does not contain a cycle of length L as a subgraph. Okay, we'll be studying mainly those graphs. Now let's get to some introduction. When we discussed the branch of experimental combinatorics, it basically started with Mantle's theorem, which is a theorem which states that, well, it wants to maximize the number of edges while having some restriction on the graphs. Yep, so, and of course we know this is n squared by 4, law of that. And in this setting, we also will be trying to maximize some graph parameter while having some restrictions. In our case, the graph parameter we'll be maximizing is the Outdegree, while the restriction is that it does not contain a cycle some set length. Yep. Why even study cycles, and what's the what's the intuition about it? Well, most of the research regarding cycles and graphs in extremal graph theory started with Grzesik conjecture, which basically states that if we have an n-vertex graph with an outdegree sufficiently large, it will have a cycle of length at most some number. The outdegree sufficiently large is just n by greater or equal n by l, and then we'll have a cycle of length at most l. In the case in the simplest case, as when L is equal to 3, this conjecture is of course still open, and we just we want to show that if there exists if there is a graph of an outdegree greater or equal 1/3 n, then it contains C3. Of course, this conjecture is still open, but there are many results, especially when we, instead of constant 1/3, put some arbitrary constant. Why it is even, well, like to give some intuition why it's so hard, I would like to show some extremal constructions which get arbitrarily close to 1/3, the outdegree 1/3, but still do not contain C3. They, as you will see, have almost no tangible structure to, like, it would be very hard for a proof to consider all of them or find some uniform argument that works for all of these constructions. So for example, there is a carousel graph, which is simply putting vertices on a cycle and then connecting vertices which are at most 1/3 of the way, like with the orientation of the cycle. And as you see, this is a carousel graph with 7 vertices. It does not contain C3. When we get more and more vertices, we get closer and closer to n by 3. This is a blow-up of iterated blow-up of C4. It still does not contain C3. And the more how iterated blow-up works, by the way, is just we have a blow-up of C4. You know how it looks. And then inside of each blob, we put another blow-up of C4. And inside of each blob of that, we put another C4, blow-up of C4, and so on and so forth. Essentially, what happens here is we can compute the outdegree as just, well, n by 4, a regular blow-up C4, plus n by 16, the inner blow-up, plus n by 64, and so on and so forth. This is exactly n by 3. I mean, it approaches n by 3, that never gets exactly to it, but in the limit it is n by 3, and does not contain C3. In the blobs, we can, for example, also put a carousel graph, or we can do some mixed strategy. Generally, it seems very hard, and it is still widely open, but we have decent results concerning that. Conjecture, for example, if we consider instead of an outdegree 1/3 by n, some constant times n, and see what constant can we, how low can we get. And there are many results. Grzesik in their paper proved already 0.38919, and we got down to recently 0.339, which is very close, but still not 0.33. Right? Yeah. So, but why you may be wondering why I even bring this up here, because we will be using some of these results later. Okay, let's discuss related problems to Grzesik conjecture. We can consider semidegree, which is minimum of the outdegree plus integree, minimum outdegree and integree, and we can just do very related conjecture to Grzesik, where instead of outdegree we put a stronger statement about semidegree. Right, semidegree is a stronger statement than outdegree. You may notice that the year here is earlier, but they only formulated the hypothesis for a specific class of graphs. The generalization came later, but it generally is simply Grzesik conjecture, but instead of outdegree, we have a semidegree. Yep. And it's of course still very open. It's a very hard problem. We may also ask what degree conditions may force an directed cycle of some set length. As noticed that the previous conjecture and also the conjecture like this only stated that there exists a cycle of length at most L, but not exactly L. They just meant that there exists a short cycle. What if we asked what conditions on degree would force an existence of a cycle of some set length? And there was a conjecture by Kelly-Kühn-Osthus in 2010, where they basically stated that there exists a very important constant for an L, which is sufficient. Let me give you an intuition about it. So say we want to force an existence of cycle of length L. Yep. And we wonder how big a semi-degree can get. Well, of course, we may look at L plus 1, and a blow-up of cycle length L plus 1 does not contain a blow-up of a cycle or blow-up of CL, and it's pretty dense. The Outdegree is pretty high. But we can do better. For example, if we want to forbid, say, C100, well, I have a very dense graph which does not contain C100 and this C3. Simply a blow-up of C3 does not contain, only contains multiples of 3. So, yeah, this reasoning we can deduce that a very important constant may be the smallest number such that it does not divide L. As then, a blow-up of CK would not contain would only contain multiples of K, which is not L. And it's very wide. So it's very, 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 very dense. The semi-degree is very big then. And they conjectured basically it. They conjectured that for any L greater or equal 4, that every big enough n-vertex-oriented graph with an Outdegree greater or equal n by k contains CL, with the extremal construction being just a blow-up of CK. You may notice here that L must be greater or equal 4 because otherwise we would. Yes, because otherwise such K may not even exist. No, sorry. Actually,
Just catch it.
oh yes, it just catch it, please. Sorry. Yes, it's not needed. Okay, and they have proven this is true for K equal 3. So if L is divisible by 3, they showed that a blow-up of C3 is in fact the extremal construction. Everything greater than n by 3 plus everything greater than n by 3 in semi-degree would force an existence of CL. But in general, and also it's asymptotically true for all K and large enough L. Asymptotically meaning that there is a lower error of lower order of magnitude with n in the semi-degree. But in general, this is not true for K greater or equal 4, proven by Grzesik and Volec in 23. Why? Well, they have shown that for these L that are divisible by 3, we may do better, meaning an oriented graph with semi-degree equal n by k plus this small little constant of k minus 1 by 2k, which is, as you may notice, it's an addition which is lower than 1. This semi-degree would force the existence of CL, where k would be the smallest integer greater or equal 3, such that it does not divide L, of course. And they had shown that for L not mod 3 modulo 12, this is the best possible threshold. Whereas for L divisible by 3, L equivalent to 3 modulo 12, then semi-degree of anything higher than n by 4 is already forcing CL. And just n by 4 is the best possible threshold. Okay? As an example, I have drawn here an extremal construction which does not contain cycles of length equivalent to 6 modulo 12. And how it works is we take a block of CK, C4 in this case, and our forbidden graph, of course, is C6, C, and where L is equivalent to 6 modulo 12. What we do is we add 3 vertices, one in these blobs and one in the middle, and we connect the middle one with the blob here and the blob here, and we take the edges from this blob to this and this blob to this one, the one in the middle. And you may notice here that every vertex points towards at least one blob and one red vertex, and is like points from also one blob and at least one red vertex. Meaning the Outdegree has increased by 1, where the number of vertices only increased by 3. Yes? So this is, for example, greater than n by 4 plus 1/4, and it does not contain CL, where L is 6 modulo 12. We cannot do this twice, for example. If we did this twice, we would have already CL. But this may be later. Why can't this proof be applied to our problem? As you know, we would be concerned with Outdegree instead of a semidegree. Well, a graph with a high semidegree has a bounded diameter, whereas a graph with an Outdegree, with a large Outdegree, may not. This is an important difference, as I think I lost my mouse, but that's fine. Yes, so and the Grzesik and Volec heavily use a lemma when they heavily use this fact that the graph has bounded diameter. We had to find a workaround. Okay, so let's get to the topic of the talk. So, Outdegree conditions forcing directed cycles. Well, it doesn't matter, it's the same. So there was one result in the past about, it basically states that if L is divisible by 3, meaning that K would be 3, then anything greater than n by 3 already forces an existence of CL. For any L greater or equal 4. Okay, so Jagiellonian University announced the problem that in 2021 that basically they have just proven the case where K is equal to 3. Well, we managed to take care of cases where K is greater or equal to 4. Okay, and what we say is that when we have an Outdegree that is slightly greater than n by k, which is equal exactly k minus 1 by k, then we would have CL where L is not divisible by 3. Sorry, L is divisible by 3. Yeah. For almost every, except a very few cases, this is also the best possible threshold. And I've drawn you some drawings that will illustrate how we increase this Outdegree by this small constant while also not creating CL. Basically, we take a blob, in this case a blob of C7, and we take a single vertex, okay? We remove it. We also choose a single vertex in some other blob. And then from a blob which is previous to the deleted vertex, we orient all the vertices towards the chosen vertex. What happens is the Outdegree stays the same, but we delete one vertex. What's the trade-off? Because there is one. Well, while trying to create this CL, we may once go back to this vertex, changing the remainder essentially by 4. Right? This creates, if we could loop around making multiples of 7. One day we may go back and now be creating a walk of remainder 4 modulo 7. Okay? So we may add once we may add some remainder to what we create. Yeah, for example, in this drawing, excuse me, the mouse, I cannot move it. In this drawing, we create on C4 cycles of remainder. What? This is 3. Going twice, it's 2. But we make 3 modulo 4. We make 2 modulo 4. Of course, we may have 0 modulo 4, but we do not have 1 modulo 4. We have deleted 2 vertices essentially for free. Okay, so notice also that this addition is twice larger than the addition that the Grzesik Volec have done in the semidegree version. This is k minus 1 by k. They had k minus 1 by 2k. Okay, so how do we prove something like that even? First, we would like to get some sort of structure from a graph. We would like to say that we are, in fact, when we are close to, yes, we would like to get some structure from a graph. We would like to say we are close to a blow-up of ck. What we do is we introduce a lemma that has slightly different assumptions. The assumption on the Outdegree is lower. Also notice that everywhere here, L is large enough. L is greater or equal to 20k squared. Maybe I will say something about this. So this looks bad, but in fact, when we grow with k, L grows exponentially, as k is the smallest integer that does not divide L. Okay, and this 20k squared becomes redundant from k equal 11 or something. Yeah, something like that. So for k greater or equal to 11, this assumption is always true. But this assumption is also needed for when we try to create a walk of, when we create CL from smaller cycles. So you will see where it happens. Stop it. Additionally, you may see that Chigrinov, Mala, Nagler, and Osthus only gave us the case that L should be divisible by 3, otherwise the C3 would be the extremal construction. In the statement of the stability lemma that I present to you, we say that L is divisible by 6. In general, we had to split the proof in 2 cases, an odd case and an even case. The odd case, unfortunately, requires more careful, more technical work. Therefore, I will present on this talk only the even case, as it's simpler. And yes, the odd case is similar, but it does require some things. If I will have time, I will say something about it at the end. Okay. Now, what I was saying before was that we needed something to create a structure to show that the graph is very close to a blob of ck. We will introduce a lemma that has different assumptions. We sacrifice some epsilon n in the Outdegree. Okay, so the Outdegree is slightly lower, but instead our constraint is way stronger. Our constraint now is not that we do not have a blow of ck. Sorry, we don't have a cycle of length L. Our constraint is that we do not have a closed directed walk of length L. Meaning, it's just a cycle of length L, but the vertices may appear twice. We may also use some edges twice. Good idea. Yeah. Okay, yes, so stronger constraints, but slightly lower assumptions. We say that this is very close to a subgraph of the blob of ck. with a very large semidegree. The framework for the proof would be as follows. First, we would like to show that there exists some special vertex that contains the special vertex, such that for any other vertex there exists a relatively short path to it. Okay. This is our workaround for the problem that we do not have a bounded diameter, by the way. From how we prove it is we will use, I will show it more detail later, we will use a bounded conjecture twist, and then build some tower of out neighborhoods, meaning just look at all vertices which are of distance at most some set distance from V. And we will show that for there exists some constant such that this tower of neighborhoods will be greater or equal n by 2. We will then construct some auxiliary graph which will help us find V0 as a vertex with a tower in neighborhoods greater by n2, and simply these two towers would intersect. I would say this in more detail in a second. But for the framework later, we would observe that for this special vertex V0, there would be no two short paths of different lengths which end up in the same vertex. Otherwise, we would create, from this other vertex, we would make a short path to V0, and we would create two closed directed walks of different lengths that cut a V0. Combining these finite number of times, like using a Frobenius coin problem, we would create a closed walk of length L. Okay? In the end, when we have that, we can show that we have a structure which is very similar to a block of CK. Then we simply need to remove vertices with in-degree which is too low, which we could do with some help of technical double counting. Okay, so that's the framework. Let's get from the general framework to details. So claim 4.3. We want to show that there exists a vertex which has a path from every other vertex which is relatively short. Okay, so we use fact from Grzesik and Volec, such that every n vertex graph with an Outdegree this constant times n contains a directed cycle of length at most 3m. This is some bound on the Cacciaheta-Quist conjecture. It's, to be honest, I mean, it is some bound. It's not the best bound, but it's not the worst. It's okay. We like it. It's enough for a problem. So it simply says that if an Outdegree is too large, we have a pretty short directed cycle. But now, notice that if we set m to be k minus 1 by 3/4, then, well, we must not have in our graph a cycle of length at most k. Sorry, we may have a cycle of length k, we may not have anything lower. Why? Because we defined k as the lowest, the smallest natural number greater or equal 3 that does not divide L. If we have some smaller cycle than k, then we have then it is some multiple of L. We may just loop around it finite number of times to create a closed walk of length L. Yes? Therefore, in our graph, we may, and in every induced subgraph of it, we must have a bounded Outdegree. Yes. The Outdegree must be bounded, but from above. Okay. So how we build a tower of out neighborhoods, and how we show that it must be large, is, well, we just define a tower as, well, the first tower is just an out neighbors, the second is just the previous tower plus the neighbors of the last. Okay? So it's simply a set of vertices with of distance at most some, in this case, I from V0, from V. Okay? And when we have this xi, notice that the outdegree, well, if the outdegree is greater than, minimum outdegree is greater than c times the size of xi, then we would, from the fact 4.2, create a forbidden cycle of length something smaller than k. Therefore, there must exist at least one vertex v in this this tower which has low outdegree to this set xi. But it has a large outdegree to the whole graph, meaning it has a large outdegree to the rest of the graph. Okay? This is the basic idea here. And we show that simply xi plus 1 is greater than outdegree of the whole graph plus 1 minus c size xi. Yep. With some help of some technical algebra, we show that simply if we plug in into I 5m, right, then it is already greater than one half of the graph. Okay. Now, what happens is when we have this, we know that for every vertex there are at least half of vertices of the whole graph, such that there is a path from this vertex to them of length at most 5m. Yes? We simply construct an auxiliary digraph, G prime, with edges if and only if there exists a path from U to V of length at most 5m. Yes, if and only if V is in the outgoing tower of U of length 5m. Now, this is a directed graph, by the way. This is not oriented. As we know, the outdegree of this auxiliary digraph, it's supposed to be G prime, by the way. Oh no, yes, it's supposed to be G prime. Sorry. As the outdegree of this auxiliary digraph is greater or equal 1/2, there must exist a vertex with indegree greater or equal 1/2. This is a special vertex because now, for any other vertex in the graph, we know that there are at least half of the vertices with an ingoing tower, with half of the vertices such that there is a path of length at most 5m from them to V0. And we know that for any other vertex, there exists at least half of the vertices. Oh, I have a. Yeah, it's basically this. We know that there is at least half of the graph with short cycles from some vertex V. And we know that at least half of the graph has short cycles to V0, so short paths to V0. So there must exist a vertex in the intersection. We have a short path from any vertex to V0 of length at most 10m. Okay? Yes. And that's it. That's it. We have the special vertex. Now, take the observation 4.3. We simply define blobs as vertices of some set length of some set distance from V0. Yes, we take V1 as the out neighbors and Vi as just the neighbors, outgoing neighbors of Ni minus 1 by simply. Sorry, this is not supposed to be Ni minus 1. It's supposed to be Vi minus 1 by simply then sum of Vi. Vj's. Yes. And the observation is simply that there are no arcs between these. I have this. That's useful. The observation is simply that when we define blobs like this, notice that we are still in the even L case, and that's where it comes. That's where it's useful. We say that there are no stupid edges between, for example, like here, or edges going backwards inside of the blobs. And why it's true is simply because we would take a short path from this vertex to V0 and we would create two intersecting cycles of different lengths. And notice that their lengths are their lengths would be sorry, not cycles, close directed walks. Yes, it would be of length d plus I plus 1 and d plus j. If, for example, there would be an arc from vi to j. And their difference is small. The difference is less than k. If they are not edges directed like they should, their difference is also not 0. Okay, so we would create some by combining them finite number of times using Frobenius coin problem. We would create CL using them. Right, when we have a coin of denominator 2 and coin of denominator 5, we would create from some point on every possible number from using some of them. Here, the principle is the same. Yes, we'd create all the multiples of their lowest common divisor. Sorry, largest common divisor. Yep. Okay, and that's the observation. And this implies that given that there are no bad edges, we can see that the size of every blob is large, because from every vertex in the previous, the only edges going out are to the next blob. Hence, the next blob is at least the size of the outdegree of the graph. Yes. Okay, and we have one remaining thing to show in the stability lemma. We just need to prove that we can remove vertices of low integrity. I will show only an idea of it, because the proof is pretty technical. But generally, we know already that we have a blow-up of a cycle of length k, and some small number of vertices which do not belong. And we also, from this, we know that every vertex has a very large outdegree to the next blob, meaning that there is almost all edges between exist here. What does that mean is, if we do some clever double counting, we also need to bound. Also, we need to know that every blob is large, meaning, and large meaning n by k plus epsilon n minus epsilon n. It implies that the integree of the graph is also bounded. Integree of the vertices here. The maximum integree. Why? Because blobs here, if every blob is large enough, and there are k blobs, then there may not be a blob of size n by k plus k times epsilon n, as we would just run out of vertices in the graph. Yes. Therefore, the maximum integree in the graph is bounded. In the blob is bounded. And we know that almost every edge exists. This implies that if we do some double counting, we can show that the number of vertices with a low integrity is very small. Yes, as we just split the vertices into low and high, and bound the vertices, the integrity in the high as the maximum integrity, and bound the vertices in the low as, well, some threshold S. Yes. In essence, that means that we may remove lower order of magnitude vertices in the blow-up, which does not change a thing to us, and now require the blow-up of CK to have a large semi-degree instead of only in degree. Cool. So that's it. That's the stability lemma. And now how do we get from the stability to the main proof? So we assume that L is still large enough and divisible by 6. And we want to show that every graph of a set Outdegree contains CL. Yes? Great. The idea is to now apply a regularity lemma to remove all close directed walks of length L while sacrificing only epsilon n of Outdegree from the Outdegree. This would allow us to use stability lemma and get structure in the graph. We would go back then, adding back the vertices and edges carefully, such that we would put the vertices in the hypothetical set of unused vertices called trash. And we would also notice some observations about, well, how many edges can we add back which do not behave nicely. In fact, we may show that we can show that in the case where L is divisible by 2, so in the even case, we can remove also the edges which are added, extra edges which are added like here to the trash set and not sacrifice too much in our structure. Therefore, we could show then that a blow-up is that we have a very large subgraph, which is essentially a block of CK. And we show that each 1 by k above n by k essentially forces an existence of what a structure we call a side. We have a block of CK. It may not have all the edges in here, but definitely most of them. And we have some center of the sidewalk. We have a large enough number of edges going from some block and large enough amount of edges going to some block. This creates is essentially like a one-time, if we loop around our blow-up of C5 in this case, we may use this sidewalk once to change our remainder modulo 5 by 3. Yes? If we were to get to CL, L modulo K, we would create CL simply by looping around this as many times as I can. That's also only a framework. I will try to show the proof in more detail soon. What we end up is a set of M vertices, M sidewalks simply, and remainders that correspond to them. These are simply just remainders that we can create using them. What happens is the sizes of these sets of remainders sum up to k minus 1. We show using some additive combinatorics. I mean, we use results from additive combinatorics to show that we may combine these to create L modulo k. By combining the sidewalks and looping around a few times, of course, it includes some technical details, but you get the idea. We may create, we use these to create simply CL. Yes? Okay. This slide I will mostly skip. I will just, this is for the sake of completeness. We use the degree form of the regulatory, regularity lemma by Andrzej and Shapira. We simply say that, it's just a special form of Shemarati regularity lemma for digraphs. In essence, focusing on Outdegree. What we then use is we use graph removal lemma. I will just maybe by converse Sarkozy and Shemarati. Basically, we remove all the homomorphic images of CL by sacrificing some epsilon n in the Outdegree using these two results. Unfortunately, I don't think I have time to say more about them. With this, as we sacrifice epsilon n from the Outdegree, to remove all the homomorphic images of CL, which are simply close-directed walks of length L, we are exactly in the statement of the stability lemma. Yes. We of course use it. We find out that we have a large blow-up of CK, and what we need to do now is we need to add back the edges and vertices. Yes, the degree version of the stability lemma says that basically we have to remove from the graph epsilon n lower order of magnitude number of vertices and lower order of magnitude number of edges, meaning O of n and O of n squared respectively, to remove all the homomorphic images of forbidden graph. Yes. Then what we simply do is we use the stability lemma. We know that we are basically a blow-up of CK with large in degree, large out degree. And we here still assume, of course, L is even. Why we assume that L is even, you may ask? Because now we may remove, we notice that, well, some edges were added, and we simply say that there are not many edges going opposite, like having the opposite direction which were added to the blow-up. Yes, edges that look like this. Why? Because they're essentially changing a remainder. We may use them to change the remainder by 2 when going around. Yes, we go to this vertex, we look back, and we go further. This changes CK to CK plus 2 once. We may not have K minus 1 of them which are vertex disjoint. In the case where L is even. Because if L were to be odd, say we have forbidden C9, say we have C9 forbidden, or C15. We state that in our case the blow-up would be C4. Yes? An edge like this would simply create another all-even cycle. This would change the remainder by 2, but, well, we could do C4. We could do, with the help of this edge, C6, C12, C8, but it is not even. The parity, unfortunately, here doesn't change, and that's why we cannot use. We have to be more technical in the odd case, because in the odd case we may have actually epsilon n squared edges going back added. In our case, we don't need that. We can just remove. We can just put the vertices that they correspond to the trash set. Okay, so by cleaning the graph, we basically have a blow-up of CK with a large in degree, large out degree, and some epsilon n's and vertices inside, which do not behave nicely. We don't know how they behave, but they cannot be added back here. Okay. And now we define what it means to be an in-pointing and an out-pointing blob. We pick a vertex from here, and we say that if this vertex has at least 2k neighbors going from the blob to this vertex, we call this blob an in-pointing vertex. An in-pointing blob of this vertex B. Similarly, if it has at least 2k, I think I have a drawing in here, but it's more ugly. Sorry. Similarly, if it has at most 2k going out, we call the blob outpointing. And basically, what we say is that a sidewalk is a tuple of. We have an in-pointing blob, a vertex in the center, and an out-pointing blob. The remainder of such sidewalk is basically if it goes from Vi to Vj, then the remainder would be I minus j plus 2. It's essentially how much would it change, would the remainder change when looping around by going this vertex. Of course, some sidewalks do not change the remainder at all. For example, the ones which go from this block to this block, right? We make this is 2 steps and this is 2 steps too. That does not change the remainder at all. We do not want to concern ourselves with these sidewalks. Therefore, we differentiate between sidewalks. We call sidewalks non-zero if it creates remainders that are not zero. Okay. Yes, and the important observation here is that if we have a set S of a few sidewalks with distinct centers, which remainders would add up to L modulo K, then this S could be combined with some edges of H prime into CL. Yes, it just means that we can combine sidewalks using short enough paths such that we create not a directed walk of length L, but a cycle of length L. The framework is pretty simple. Say we want to combine a sidewalk of a center with V2 from V2 to V1. And we have some edges, some vertices already used in the graph. We know that there are large enough amount of edges going from V2 to the blob, greater or equal to K. And we know that every outdegree, the outdegree is larger than half. We know also that there is a large number of vertices going from the blob to V1. And we know that the indegree of every vertex by the stability lemma is large. So we simply go forward, go back once. We have more than 1/2 of all the vertices in the blob. And we simply make a path to the blob before it. We look at the outdegree and the out neighbors and the in neighbors intersect, as they're both greater than 1/2 of the blob. And that's simply how it creates, how we combine the remainders. Yeah. So now let's get to, let's finish the proof. So we want to show that G contains a set of less than K sidewalks with distinct centers whose remainders add up to L modulo K. Because this, from the previous observation, would imply the existence of CL. This is, by the way, also a part where we use the assumption that L is large enough. As otherwise, notice that when we were combining these, we may sometimes not be able to, we may sometimes need to loop around the whole graph, the whole block, okay, to go back to the previous. This essentially implies a soft bound that this method can provide of, well, we have K-1, we may loop around up to K-1 times, so the soft bound would be around K squared. We have shown that 20K squared is sufficient. So there is some values of L in between, but generally there must be bound to this method. Yeah. So how do we prove that there exists such set of cycles? And this one is actually pretty fun. So we look at the vertices in the set, the trash set, right? The set T, and we basically want to remove. Yes. Let's first, for vertex T in T, say that Z of T is the number of in-pointing blobs to T. As T has at least one out-pointing blob, then T must create at least ZT-1 non-zero remainder sidewalks with center T, of course. Yes, because we create ZT sidewalks simply as in-pointing, from every in-pointing blob to out-pointing, we can create a sidewalk, and only one of these can be zero. So ZT-1 non-zero ones. They're of course also all different. Okay, and now for each blob, and vertex T in the trash set, we look at vertices that are connected to it. Well, we basically want to remove some set of problematic vertices from every blob. And what we mean by problematic, well, what would be problematic? If we would have a vertex, an edge from a blob to T, but the blob would not be in pointing, because this would make the analysis way harder for us, make all the technical work way longer. Fortunately, such vertices, well, we know that there must be at most 2k minus 1 such problematic vertices for set T. Because if there were 2k of these, well, the blob would be in pointing from the definition. Yes, so every T creates at most 2k minus 1 problematic vertices in each blob, which are going in, and at least 2k minus 1 vertices in each blob which are going out. So the size of X, which are the size of problematic vertices, is also bounded. So this should not be 2k, it should be 4k instead. It's bounded by 4k epsilon n for every blob. But this is generally pretty small. This is some lower order of magnitude to n. Yes, so notice that for each vertex outside this problematic set, if this vertex has some edge to a blob in the trash set, if the vertex outside of X in a blob has some edge to a vertex in T, then in fact this whole blob is in pointing to T. Yes, and that's a very important observation. As now we don't need to look at quantitative methods. We don't need to try to quantify how many edges go from vertices in the blobs general. We may just choose one blob outside of the problematic set. One vertex outside of the problematic set for every blob, and try to do analysis on that. Yes, so we show that in each blob, we show that in each blob there is a problematic set. And simply choose one vertex in each blob outside of X. Yes? Now sum up its outdegrees. We have k vertices outside of X here. We sum up the outdegrees, we get n plus k minus 1. Simply n by k plus k minus 1 by k times k, right? The minimum outdegree times k, just at least n plus k minus 1. But notice that, say we have chosen these vertices. Notice, we know that the sum of outdegrees from them is at least the size of the whole graph plus k minus 1. We know that each vertex only has edges to the trash set and to the next blob. Yes? So the vertices in each blob are counted exactly at most once. Therefore, there must be at least t plus k minus 1 edges from these special vertices we chosen to the trash set. From using some pigeonhole principle, we simply show that, right, because a few vertices must get 2 edges going in. A few vertices must have 2 in-pointing blobs. In fact, this simply implies that the sum of ZTs is at least t plus k minus 1. What is the sum of zt minus 1, which is the number of notice that this is just the number of sidewalks of different non-zero remainders for vertex t. Sum of zt minus 1s is greater than equal than k minus 1. Okay? And this is already enough. We know that we have some vertices which create non-zero remainder sidewalks, And the number of these sidewalks is at least k minus 1. They may have joint centers, but it does not matter. What matters is that this, using some additive combinatorics, we simply can show that we may use some of these and create CL. And that's basically what we do. Yeah. So I will say a very few words about the odd case and the special cases, but this was the main proof we have done. So about the odd case, what's different is, well, we assume that what we are left with the case that L is 3 modulo 6, because 3 not divisible by 3 is 3 not dividing L was solved by Jagiellonian, right? So the stability lemma, unfortunately, can only provide us with a bipartite graph. What we need to do is we need to show that we are very close to a blow-up of C4. We in fact can do it, but it requires slightly different reasoning. So so notice that when we were creating the blobs using the stability lemma, this time we cannot remove edges going backwards, or yes, basically we may not remove edges going backwards because we have forbidden a closed walk of an odd remainder. Sorry, simply some odd closed walk, and this simply can be an even cycle, and this can simply be an even walk, and this can simply be an even walk. We will not create anything problematic with it. Yes, well, we only can forbid edges from blobs of the same remainder. We can forbid edges from odd to odd. We can forbid edges from even to even, because then, of course, we would create something odd and something even. We may create everything using the Frobenius-Kohn problem. So the stability lemma only gives us a bipartite structure, but when we get more careful, we can show that, in fact, we are almost a blow of C4. Why? We show that find a vertex which, because the remainder is greater, the Outdegree is greater than n by 4, greater than n by 4, then there must exist a vertex V with one edge going from some blob from one side and one edge going to the other, simply by the double counting, simply by numerical reasoning. And why is this vertex important? Is we look at we find one that has a large integer here, meaning that D is large. We create simply a greedy path of length, I think, L minus 3. We end up at some vertex with a large Outdegree. What happens is that there are no edges from A to D. Okay? And A to D are large enough. They are n by 4, plus minus some lower order of magnitude, depending on it. Yes? And the existence of such structure is already enough for us. Because if there are no edges from A to D, every edge going from A must go to B. Yes? As every edge from A goes to B, this is almost full. There are many, many edges here going out. Therefore, there must be very few edges going back from B to A, as we just simply would run out of possible edges. But with this reasoning, we can show that as there are few edges going from B to A, there must exist a lot of edges going from B to C. So there must be few edges going from C to B. Hence, there must be a lot of edges from D to C. So from C to D. And so on. You cannot have many edges from D to C, then we must have a lot of D from D to A. And that's basically how we get this structure using more careful reasoning. And that's just a sketch of it. Okay. And last word about special cases. We had shown that the bound of n by k plus k minus 1 by k is sufficient for basically all L. Well, apart from the ones not divisible by 3, because then Jagiellonian Osthus and I forgot the last one. But they had problems, yes? So what we are left with is, it turns out that in a few cases, an Outdegree lower than that is already sufficient for existence of CL. Where it comes from is that if you remember how we made an extremal construction, we had to choose some vertex. Had we chosen a vertex in the same blob, or as the removed one, or in the same blob as, had we chosen this vertex in this blob or this blob, meaning remainder 1 or remainder 2, this would be very problematic, as well, its Outdegree would not be sufficiently large. Hence, we may not create all the that does not exist in an extremal construction like we did for every remainder modulo 60, because we only work about L divisible equivalent to 6 modulo 12 and equivalent to 24, 48 modulo 60. So these are the problematic remainders. We had shown that for L, which is equivalent to 6 modulo 12, an Outdegree greater or equal 1/4 less than what we previously expected is already sufficient for an existence of CL. And for L, which is equivalent to 24 modulo 60, an Outdegree greater or equal 1/5 lower than what we expected is sufficient for creation of CL. We had shown also that these bounds are the best possible using very technical reasoning. And currently we're working with Andrzej on proving that L equivalent to 48 modulo 60, so K is 5, and the remainder of L is 3. Yes, 3. Yes, I had to check that 48 modulo 5 is 3. That if L equivalent to 48 modulo 60, then the bound 2/5 lower than what we expected is the best possible. And yes, I'm pretty sure we can prove that. That we have to combine a lot of things. We are working currently on it. And yeah, that's pretty much it. Thank you for your time.